Assalamualaikum and good morning to my friends and Dr. Halim. Thank you for joining me today as we embark on a fascinating journey into the world of geophysics, specifically exploring the concept of deep move-out correction. Geophysics is a discipline that enables us to unravel the mysteries of Earth, uncovering its hidden structures and resources using various techniques and technologies. Deep Move Out, commonly known as DMO, stand as a crucial and transformative method that significantly enhance seismic data processing and interpretation. In this presentation, we will delve into the fundamental principle of DMO, its application, and the impact it has on seismic imaging and subsurface analysis. But first, let's set the stage by understanding the fundamental challenges geophysicists encounter during the seismic data processing. Seismic data processing provides us with a wealth of information about the Earth's subsurface. However, this raw data often contains inherent complexities due to the factors such as irregular topography, velocity variation, and subsurface heterogeneities. One such complication is the phenomenon of the travel time anomalies that is caused by the reflection from the dipping subsurface of the interfaces. These reflections are not accurately positioned in the seismic data, leading to distorted images and loss of resolution in the subsurface structures. So without further ado, let's carry on this educational presentation together as we explore the wonders of deep Moveout in geophysics. Throughout this presentation, there will be 10 chapters that will be covered by me. The first will be introduction. The second is the problem statement. Third is the main content. Fourth is the main people working in the research. Fifth is the recent major advances and discoveries. Sixth is the significant gaps in the research. Seven is the current debate of the research. Eight is the DMO research in the future. 9 is the conclusion and recommendation. And lastly is the citation and references for this case study. Now let's proceed. We will start first with some introduction of deep move-out correction. Deep move-out is a revolutionary technique that corrects these travel time anomalies and enhances the quality of the seismic data, allowing us to extract valuable insight from the Earth's interior with greater precision. By compensating for the dip of the subsurface reflection, DMO aligns seismic event correctly, leading to improved subsurface imaging and clearer understanding of geological features. Throughout this presentation, we will uncover the mathematical principle behind the deep move-out correction, explore the different DMO algorithm used in the practice nowadays, and demonstrate its impact throughout the real-world case studies. Moreover, we will touch upon the recent advancement in DMO technology and how it continues to shape our geophysical landscape. Next, we will proceed with the problem statement of the research itself. During the acquisition process, Seismic we've traveled through the complex geological formation, encountering various obstacles and challenging velocities. The result is often a collection of seismic traces that are plagued by irregularities, misalignment, and undesired shift in travel time. The primary reason behind these seismic data anomalies is the phenomenon known as deep move-out, or also known as DMO. DMO is a consequence of reflection from dipping subsurface interfaces, causing the travel time deviation from their actual position in the data. This distortion introduces inaccuracies, limit resolution, and obscure critical geological features, which prevent geophysicists from obtaining a clear and accurate understanding of the subsurface. The problem is also not merely theoretical. It also directly impacts data interpretation and consequently critical decision made in exploration and resource assessment project. Inaccurate seismic imaging can lead to misguided drilling and exploration efforts, so which result in substantial financial losses and inefficiencies in the energy and mineral sectors. Next is the main content of the research itself. So here we will explore the theories, the equation behind the DMO correction, and many more. So in theory, flat versus dipping subsurface. In a flat surface, the layer of interfaces between the rock formation are horizontal and parallel. When a seismic wave encounters this horizontal subsurface, it reflects towards the surface, creating a simple and straightforward seismic reflection pattern. So some of the key features on a flat subsurface are horizontal reflection, constant travel time, uniform amplitude, and constant dip angle. While on the other hand, in a dipping subsurface, the interfaces between the rock formation are not horizontal but inclined at a certain angle to the horizontal plane. This introduces some complexities in the seismic reflection due to the depth of the interface. Some of the key features in seismic reflection in dipping subsurface also include non-horizontal reflection, variable time travel, amplitude variation, and also variable dip angle. So here are the equation that will be used to correct the phenomena known as DMO, which says delta equals to x squared over d times cos theta sin theta, where the delta is moved out deep, x is the half source receiver offset, d is the depth to the reflector at midpoint, theta is the reflector of the local dip. So the DMO equation compensates for the effects of dip by removing the distortion caused by reflection from dipping interfaces. The application of this correction is crucial for obtaining accurate seismic images and reliable subsurface information during the seismic data processing and interpretation. So various DMO algorithms exist, so each tailored to different geological scenarios and subsurface structures. It is important to note that there are different variation and extension of DMO equation, not only one. This is just the general term, so which function to accommodate more complex geological scenario such as anisotropic media, multi-layered model, and converted wave. These variation introduce additional parameters and terms to account for the specific geological parameters and many considerations. Here we can see some of the field data in Gulf of Mexico before and after the Moveout correction. The left is before and the right hand side is the corrected seismic trace. Beside the Gulf of Mexico, we can see the field data in salt body, which is very clear. On the left hand side, we can see the salt body appears not too visible and many corrections need to be done. On the right hand side, we can see a clear and visible salt body in the subsurface imaging. Now let's move on to the next chapter, which is the main people working on this research. So DMO has been a crucial seismic data processing for several decades, and many famous geophysicists and researchers have contributed their development and application towards this study. So some of the main famous people for their work in DMO is Dave, which Mr. Ira Dave Hale, which received the Virgil Kaufman Gold Medal from the Society of Exploration Geophysics (SEG) in 1989 on his work on deep Moveout processing on seismic data. He also taught the SEG first course in deep move out processing as the part of SEG continuing education program, and also the editor of DMO processing volume 16 of the geophysics preprint series. Next, we also have Mr. John F. Clairbout. John Clairbout was renowned geophysicist and professor at Stanford University. He made a significant contribution to the seismic data processing and exploration geophysics. Clairbout work on DMO and seismic imaging algorithm had a profound impact on the field of geophysics. Next, we will proceed with the recent major advances and discoveries in DMO research. So here are the recent major advances and discoveries that I have found during my research. So there are two of them. The first is DMO in converted wave imaging. So with the increasing complexity in exploration target, the DMO methods could no longer meet the exploration requirement of the complex structural exploration area. So DMO in converted wave imaging are introduced. So this technique has been extended to handle converted wave, where the seismic wave convert from one mode to another as they interact with subsurface interfaces. This extension has improved the imaging of subsurface structures and improved the characterization of anisotropic properties. Next, we have the oriented time domain imaging, which offers significantly faster processing compared to the previous techniques that relying on velocity analysis. So it also avoids the problematic loop between the deep dependent and deep independent velocity present in the classic DMO algorithm. Next, we'll proceed on the significant gaps in the research. So here are the significant gaps in DMO research. The oldest paper is in 1984 that I have found by Mr. Hale, which titled Deep Moveout by Fourier Transform. In the paper, it says that it corrects for the deep dependent move out and allow for stacking of reflection. Next is, he says that the DMO by Fourier Transform is a method that provides accurate results for all offsets and dips given the constant velocity. And one of the newest papers in this field of study of DMO is in 2017 from Mr. Javad, which entitled the Oriented Time Domain Deep Move Out Correction, which is the same as the last slide. So like I said, it offers a significantly faster processing and also avoid the problematic loop between the deep dependent and deep independent. Now we will move on to the current debates of DMO research. The ongoing debates revolves around the effectiveness of the existing DMO methods in handling complex geological scenario such as anisotropic media, multi-layered model, and area with sharp velocity variations. So researchers may discussing the limitation of current DMO algorithm and exploring ways to improve their performance in such challenging environment. Next is DMO correction, particularly in 3D seismic data, can be computationally intensive and time consuming. So there might be a debate on finding the right balance between achieving higher accuracy through advanced DMO and maintaining the computation efficiency for practical application. Next is the DMO research in the near future. So in the near future, we can see the integration of machine learning and data-driven methods into DMO. That is very significant in our future. So researchers may explore using this technique to optimize DMO parameters, automate the correction process, and improve the overall efficiency and accuracy of seismic data processing. Next, with increasing the demands of the real-time seismic data in various applications, future researchers may focus on developing real-time or near real-time DMO algorithm that provide rapid and accurate correction for seismic data analysis. Now we are approaching the second last chapter of this presentation, which is the conclusion and recommendation. So to summarize my presentation today, we can say that DMO is a fundamental and essential in seismic data processing. DMO enhance the accuracy and resolution of seismic data, and DMO has undergone significant advancement. Some recommendation that we can say about this research is that it can be continued research in a complex geological scenarios, which is in modern exploration nowadays, and we can implement machine learning in this DMO research and also the real-time DMO processing. On to the last chapter, which is the citation and the reference for this research paper. So here are some of the citation and references that I have used throughout this presentation. So we can see about 10 of the references. So that's all from me for my presentation regarding the deep move out correction. So thank you for listening and see you next time.